Well, welcome to the Explainer. Today, we're embarking on what I can literally only describe as a cosmic detective story. For centuries, mathematicians have stared at prime numbers, basically treating them like this unpredictable, almost chaotic sequence, just randomly scattered across the number line. But what if we've been looking at them entirely wrong? What if we aren't just looking at abstract math, but instead we're looking at a highly structured, hyper-efficient mechanical system? Because today we are going to actually reverse engineer the universe's motherboard. We're going to look closely at a mechanism known as the arithmetic clock and prove that prime numbers operate as literal firmware.
Okay, let's just dive right into this. Here is our instruction manual for today's explainer. We'll start with the prime firmware, move into the Stieltjes pipeline, then cover the three laws: Law I, the wall; Law 2, aperture frontier; and Law 3, beat spectrometer, before wrapping up with reading 48 zeros. Let's get to it.
Section 1. The prime firmware. Let's talk about this universal update.
So, to actually understand this machine, we first need to completely throw out our preconceived notions about what prime numbers are. We've got a massive paradigm shift here. The old view treats primes as a distribution, right? Just a random sequence you try to find patterns in using statistics. We need to completely discard that. The new view, which is validated by the source material we're exploring today, reveals that primes are a universal firmware update. They are physical machine code feeding directly into the foundational hardware of the universe. We are absolutely no longer just doing math on a blackboard. We're looking at literal instructions that tell a physical system exactly how to construct itself.
So, the crucial point is, how does this firmware actually input data into our machine? Well, it does this through something called von Mangoldt values. Now, if you've studied number theory, you probably know the von Mangoldt function spikes only at primes and prime powers. But in the context of our machine, you really should visualize these values as tangible, physical data pegs. The machine itself doesn't actually care about the prime numbers, it cares about these specific weighted resonances. These raw pegs feed directly into the computational machine. They are the actual physical data driving the entire process.
Moving on to Section 2. The Stieltjes pipeline. Think of this as our computational read head.
Now that we have our raw data pegs, how does the machine process them? We kind of need to treat this pipeline as a physical computational read head. Let's see how this builds step by step. First, our raw prime data gets fed into the system to populate a highly structured grid called a Hankel matrix. From there, the machine performs a sort of mathematical peeling process, a Colexy factorization, extracting a recurring pattern from the data. And finally, that spits out the Jacobi matrix, which is what we call the clock. It's basically this mathematical gear system compiled entirely from our prime data. It's a literal physical translation from raw arithmetic into a structured oscillating clock.
But this brings us to what is probably the strangest, most fascinating feature of this reverse-engineered hardware. Think about this for a second. What happens when a machine has no center? If you build a physical mechanism where the central axis is just missing, what does the machine actually do?
Well, the answer is it oscillates, and our mathematical clock does exactly this. Because of a fundamental symmetry in the prime data, specifically the functional equation that makes the zero measure perfectly even, all the odd moments completely vanish. In our Jacobi matrix, this acts as a literal opcode, an equals 0. This opcode physically deletes the main diagonal of the matrix, so you're left with a machine that has absolutely no center, only edges. And a machine with only off-diagonal logic is mechanically forced to oscillate. It generates a natural rhythm, a period 2 beat, simply because its center has been mathematically hollowed out.
Which brings us to Section 3, Law I, the wall, our literal zero counter.
Now that we have a ticking clock, we need to understand the physical constraints it operates under. As our machine processes the prime data through that Hankel matrix we mentioned earlier, it eventually hits what's called a positivity wall, a point where the math literally breaks down and drops below 0. But actually, scratch that. This isn't a failure or a bug. It's an instrument. The wall law proves that this breakdown point is actually a literal zero counter. It self-reports exactly how many Riemann zeros the machine can currently see based on the precision of your input. It essentially hands you a certificate saying, hey, with the exact data you gave me, I can perfectly resolve exactly this many zeros before I run out of resolution.
All right, Section 4, Law 2, the aperture frontier. Let's look at the capacity limits. So, if the machine is limited by the precision of the data we give it, exactly what is that limit? Well, check out this incredibly specific number, 6.64. In the world of our arithmetic clock, this isn't just some random decimal.
It is a hard, physical constant that completely governs the entire computational substrate.
Running this clock requires a very strict precision budget. 6.64 is the exact multiplier. Think of it like an exchange rate between your decimal digits of precision, which we call p, and the capacity of readable zeros. If you want to buy more zeros from the machine, you have to literally pay for it in digits of precision. For every digit of precision you feed into the pipeline, the machine can hand you back information on roughly 6.64 Riemann zeros. It is a strict, linear, Landauer-style physical cost for extracting information directly from the universe's firmware.
Section 5. Law 3, the beat spectrometer. We've got 3 channels to look at. But what exactly is the machine outputting, right? Remember that period 2-beat caused by the machine having no center? Well, it turns out that rhythm is a highly sensitive 3-channel spectrometer. And this brilliantly illustrates how it works. The base level measures the gap edge, the exact boundary of the zero. As the beat climbs, the drift maps perfectly to the density profile of the zeros. And that slight wobble you see, that is a direct measurable readout of the quantum-like GUE fluctuations, the chaotic ripples in the data. The gap itself is literally the mechanism of the clock, and the rhythm it generates reads out the most incredibly complex spectral features of the primes in absolutely perfect detail.
Finally, Section 6. Reading 48 zeros. This is the ultimate payoff, the real magic trick.
So all of this theory leads us right to the ultimate payoff, the moment the magic trick is finally revealed. The researchers ran this Stieltjes pipeline, this arithmetic clock, using only raw prime data. They fed it the von Mangoldt values for just the primes from 2 up to 59. That's it, nothing else. And what did the machine output? It perfectly reconstructed the first 48 consecutive Riemann zeros to astonishing sub-gap accuracy. Let me just repeat that because it is absolutely mind-blowing. They used exactly 0 Riemann zeros as input. They only fed the machine a handful of prime numbers, and the machine's internal clockwork perfectly generated the Riemann spectrum entirely on its own.
Which brings us to our final, mesmerizing conclusion. This entire explainer proves a profoundly deep reality about the mathematics of our universe. As the source material so perfectly states, primes are not a distribution, they are a universal firmware update, and you just reverse-engineered the compiler. The Riemann hypothesis, the distribution of primes, these aren't just abstract mathematical mysteries anymore. They are the measurable, physical outputs of a tangible computational machine. You just have to know how to read the clock. And honestly, if the very fabric of our mathematics operates on compiled, physical machine code, the only question left to ask is who or what wrote the firmware.